content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation,
Chrome tab.
or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
All right. Hello. Welcome to Godel, Escher, Bach, a mental space odyssey. My name is Justin Curry. And
how old are these lectures? 12 years.
I'm a senior in mathematics here at MIT. I've spent the last year at Cambridge University in UK, and the summer before that living in Germany. So it's kind of a reverse culture shock coming back, but I'm excited to teach Godel, Escher, Bach again. I taught this course in spring 2006. It was a 10-week course then, and we attempted the impossible task of trying to get through this thick monster all in one go. And it's impossible. Most undergrads can't get through it in 13 weeks. I got through it in about 7 years. So you're going to be attempting a feat here, not to complete the entire book, but to get the essence of Godel, Escher, Bach out. But I want to make sure we introduce everybody, just to get people's names. This will help me take attendance, and it will also I also want you to say, what is it when you read the course catalog that interested you most, and why, essentially why you're sitting here today. I'm curious. So what is the idea behind this book? I interviewed a good many of you this morning, and just to make sure that you guys felt comfortable with mathematics. This course isn't directly about mathematics. There's a lot of mathematics being talked about. Yes, you have a question?
What's that about?
Okay, so that's what I'm going to go through right now.
What the bro, like, the heck?
Here is that Douglas Hofstadter is interested in one primary question. And that question is, how does a self come out of things which have no selves? How is it that all these carbon atoms and molecules and proteins which make us up in the physical universe, how do they go from being meaningless to developing into an entity which can refer to itself? Like right now I'm saying, I think this, I think you like this. I'm meeting all of you as individuals. Each one of you claim to have a self. You might remember Descartes' famous quote, I think, therefore I am. So it seems like the I, when I say the I mean the things we call ourselves, as a real existent thing. But it's a complex question. How do we get I's out of non-I's? And that's kind of going to be the goal over here. So I'm just going to call it I. But how do you get to an I? You get to an I by having a bunch of meaningless primitives, things like atoms, proteins, molecules, I should say, if I want to, etc. Like this is what you're made up of, but none of these things mean anything. None of these things have eyes or selves, but you do. So what's the relationship here? Douglas Hofstadter, he wrote this book back in the 70s when he was doing graduate school in physics. And this was after him doing math undergrad at Stanford. He believed that he saw the answer when he was playing around with mathematics and the very formal systems we play with. Like when we write down things like 2 + 2 = 4, these are just symbols. And as we go through today, I'll show you completely equivalent ways of doing addition, which will look like this. And these are just logical primitives. Like, and if you've seen any set theory, and don't feel scared if you haven't seen any of these symbols, but like there exists an X for every. We give these interpretations, but the idea is that mathematics can be reduced to a bunch of meaningless operations, just symbol shunting. But what's interesting,
Haven't heard that expression in a while. Symbol shunting.
Is that
shunting around symbols?
mathematics, there exists an equivalent to self-reference. This is a bunch of atoms and proteins referring to itself, calling itself an I. What happens here, and this is going to be kind of underneath the name of Godel. Is we're going to get to some incompleteness theorems. We're going to get to some statements which in mathematics refer to themselves. And the question of how this happens, we understand this rigorously. Mathematicians have worked out how do we go from meaningless symbols to something which refers to itself and which has meaning. The claim then is that these two systems are equivalent. And this is really the profound idea. I'm going to draw this symbol, and I'm going to use a term called isomorphism. And isomorphism is basically an equals to, and equals in a different sense. But the idea here is, in many ways, we can link atoms and proteins to kind of logical symbolic primitives in mathematics, and we understand how we get self-reference in mathematics. So maybe we can use this to understand how we get I's, how self comes out of non-self. This is a really tall order, but we're going to try to do it, and that's what this book attempts to do. And what I've done is isolate the chapters in this book, which I think are most pertinent to this string of thought. But basically what we're going to do is we're going to learn how it works in mathematics. We're going to go from logical primitives and work up to self-reference and talk about Zen Buddhism, consciousness, etc. But that's going to happen as we leap over here, because we're going to work up, down, and then around. And we'll conclude the course with some interesting questions about artificial intelligence and how intelligent things come out of unintelligent things. So, when I was teaching this course 2 years ago, or 2 springs ago, I ran into kind of 5 things which I viewed as really important tools for thinking.
He was 22 years old, and he was teaching the course 2 years ago, like already. And he was like, it's weird.
And this is kind of, I've had to condense a little bit into my famous Tools for Thinking lecture. The idea here is that Godel, Escher, Bach has an incredible number of conceptual tools for thinking about this complex problem of how do we go from a non-self to a self. And just to outline these real quick, we're going to have isomorphisms, and I'll explain all these terms as we go on. Recursion. I'm going to leave this one mainly up to Curran on the second lecture. Paradox. And this is infinity, and all these concepts are very closely linked. And finally, the main subject for today's lecture is going to be formal systems. Alrighty. So, first, let me go through kind of definitions of these terms. An isomorphism, I want you to all be very careful with this, because when you start talking to mathematicians, grown-up professional mathematicians, they're going to use the term isomorphism to mean something very, very specific. The way it's used in Godel, Escher, Bach, the way it's going to be used in this class is very loose. We're going to make very kind of intuitive statements like, what's the isomorphism between a car? I'm not a great artist here. What's the isomorphism between a skateboard and a car? And you might say lots of things like it carries a person. It has 4 wheels. So what we do is we construct a map which also has an inverse. And that's the way you think of an isomorphism. You can go either way. And preserve information, preserve kind of structure. If you really feel like following along, I've included actually a quote from Douglas Hofstadter, and on page 7 of your lecture notes. He says, and this is in the middle of the page, the word isomorphism applies when two complex structures can be mapped onto each other in a ways that to each part of one structure, there's a corresponding part in the other structure, where corresponding means that the two parts play similar roles in their respective structures. This
It's like an analogy.
is how we're going to always use the term isomorphism in this class. If you're taking the abstract algebra class, it's going to mean something a lot more specific, and you're going to have a lot more details. You might actually think of these as kind of what I'll say, but don't worry about it, is a homomorphism. And the idea with the homomorphism is that there are a lot more details here than there are here. And for example, there's no steering wheel. There's a steering wheel in a car, but there's no steering wheel specifically in a skateboard. So if you were to create a map from the car to the skateboard, that detail would have to go somewhere else. But don't worry about those necessities. But when I say the term isomorphism, think of equals, and I'll often use that symbol right there. So this is going to be really important because it's going to be how we're going to get meaning out of things. And you'll see it a lot coming up over the book. But first I want to hop on and talk about recursion. Recursion is basically, it's seen everywhere, but it's kind of a list of instructions which you follow, but then repeat until you've reached kind of a final case. So suppose you're cooking and you could have a recursive algorithm for stirring eggs, and that would be whirl, and then whirl again, and keep whirling until essentially everything looks mixed up. That's a very loose way of understanding it. But another way, which you all are probably familiar with and much more rigorous in the term of mathematics, is the Fibonacci sequence. This is where you start with two numbers, 1 and 1, and then you construct the next number by summing the previous two. So you have that, and you have 3, and you have 5, and you have 8, and so on. And you can create what's called a recursive definition, where you define the nth Fibonacci number This is for n greater than or equal to 2. And here you define the thing in terms of itself. And this is a classic example of recursion. What it is really itself on a smaller level. I think one of the most exciting applications of recursion are fractals, because the way we create fractals is through recursion. So I don't know if you all have seen this, but the Sierpinski triangle or the Sierpinski gasket is kind of a classic fractal. Here you divide a triangle up into 3, and then you just repeat the process for an infinite number of times on each remaining triangle. And you create these very beautiful kind of mosaic forms. But the nice thing about mathematics is that we can be very precise and do things which we can't do in the real world. And that's repeat this infinitely, and so on. Just for a quick digression, and I really don't want to spend too much time on it because Karan will do more. Why is it called a fractal? Does anyone know?
I think it's like a fragment of something.
Sure. It was a term coined by Benoit Mandelbrot in 1977, I believe. It actually
Mandelbrot. Never heard it pronounced that way. I thought it was Mandelbrot, but I like Mandelbrot better.
refers to its number of dimensions. So this might be kind of a mind-bending concept for most of you, but we like to think we live in 1, 2, or 3, or 4 dimensions, all integers, right? But my claim is that the Sierpinski gasket actually lives in between. 1 and 2 dimensions. It lives in like 1.63 something dimensions. But I want to help you kind of think about that. And if you want to hop along to page 9, kind of got a recipe for helping you think about dimension. You know what? It's weird because only mathematicians would ever worry about rigorously understanding the concept of.
All right. It's a little weird. Like this guy's like tone is starting to rub me the wrong way a little bit.
Dimension means. So here's one way to think about it. If you take a line and you double it, you have 2 copies of the line that you started with. This guy's here and there. If you have a square and you double the sides of the square, you have 4 copies of the original square.
Wait, what? We double it. What? Huh?
Square. This guy's here and there. If you have a square and you double the sides of the square.
Double the size. Yeah, I mean, we're doubling the area of the square. Yeah, okay, fine. Fine, we're doubling this. Okay. Yeah,
You have 4 copies of the original square.
okay.
Similarly, and I'm not going to try to draw this because it will get too complicated way too fast. If you take a cube and you double each of the sides,
Like 8 cubes.
you get, if you think about it, 8 copies of the original cube. So if you're perceptive enough, you might kind of realize this action of powers going on here. So here we had, after our doubling process, 2 copies. We had 2 to the 1. Here, after our doubling process, we had 2 to the 2.
Why is it 2? Why is it 2 to the 1? So it's weird that he's doing like 2 to the 1. You can just go like 1 to the 1 or like 1 to the 3. It is still 1, but like the units are different. I mean, I guess if you call this like a length of 2, then he's saying the extra amount is 2 to the 1. It's not like the total area is 2 to the 1. 4. You have 1, and I guess you've got 4. Okay, I guess he's just describing the size of each of these. So I guess if this was 1, this was an area of 1, then we would get 4. Square it. Cube it.
After our doubling process here, we had 2 to the 3. 8. So this is weird because notice that the cube lives in 3 dimensions. And the square lives in 2 dimensions. And the line lives in 1 dimension. So this might suggest to you the relationship that 2 to the d, where d is the dimension of the space you're living in, equals the number of copies you have after the doubling process. So let's return to our friend the Sierpinski gasket. If we start here and we imagine doubling each of the sides of the Sierpinski gasket, here and here, we're very strangely led to the conclusion that whatever dimension the Sierpinski gasket lives in, it obeys this rule. So take the logarithms and d times, sorry, this is getting crowded. If you take the logarithm of both sides and solve for d, you'll see that the dimension of the Sierpinski gasket is log 3 over log 2, which is approximately 1.585 on to infinity. So here's an exact example of something which lives somewhere between 1 and 2 dimensions. And I think that's a really cool concept. Moving on for other
Way too dank.
for thinking, we have paradoxes. Paradoxes come in all sorts of different flavors. I don't know if some of you have heard of the birthday paradox, where it's the idea of, okay, what's the probability that
1 second.
someone else in the room has your same birthday? Everybody thinks it's really small, but if you actually work out the mathematics, turns out you actually have a good chance. If you're in a room with over 40 people, you have an extremely high chance of finding someone else with your same birthday. So I've actually...
No, that's not. It's not you. It's just the chance that any two people. Is it? Maybe that is
it
right.
out. This is courtesy of Wikipedia and Mr. Quine. We have sort of three variants of we have three variants of paradoxes. This is veridical, and these are things which are true, but they seem paradoxical at first. There's falsitical.
All right, I'm gonna pause it here. I'm gonna end it here. Thanks, guys, for hanging out. We'll see about this. See ya. Peace.